from Paris, and he's going to talk about an oscillatory kinetic model for the brine aggregation process.
Thank you. So first of all, I'd like to thank the organizer for giving me the opportunity to talk. So I will present today an oscillatory kinetic model for the brine aggregation process. This work is in collaboration with Marie Doumik from INRIA and Uman Rezai from INRA. Okay. So first, I'd like to introduce what we are studying. So we are studying the brine diseases. The brine diseases are neurodegenerative diseases which are caused by the misfolding of proteins. So this represents the 3D representation of the protein. This is like a normal protein of PRPC. The main disease we will study is like the scrappy disease. For example, we have there exist other neurodegenerative diseases which are brine diseases, which like Creutzfeldt-Jakob or the MADCO disease. We are only interested in the scrappy disease, okay? So the scrappy disease is caused by the PRPC protein, which transform into an infectious form of the protein, the PRPSC. And this is like the 3D conformation of the PRPSC. And afterward, the PRPSC will start to aggregate, to polymerize, and form fibrils. So here is like an atomic force microscopic images of PRPSC fibril. We can see that the structure of the fibril is essentially composed in a monomeric form which elongates the fibril at the ends of the fibril. So in the mid-70s, Prusiner proved that there is like a positive correlation between the concentration of fibrils in the central nervous systems and the contraction of the disease. But it's still like there are still few information about this kind of disease, how they degenerate the neurons, and etc. Okay. So what kind of data can we obtain from the biochemists in order to study the disease? So we can obtain static data, which are images. But what we are interested in is like in the evolution of the size distribution of the disease, of the proteins. So in order to obtain like a dynamic data on the proteins, the only experimentation I know which give this kind of data is a static light scattering experimentation. So what is a static light scattering experimentation? SLS in short. Actually, you put like fibrils at a certain amount of concentration in a test tube, and then you project like lights on it, and then you have receptors, and you capture the receptors, the lights out of the test tube, and then, okay. So the data is the light intensity. How is it composed? So what we get at the end is like an aggregate of the number of objects expressed in concentration in mole per liters, and also an aggregate of the I times the mass of a monomer. And so we can say that the light intensity we get is like kind of a second moment of the concentration of object of size A. So this, by the way, this graph is like a SLS experimentation with the initial concentration at 1 micromole per liter. And what we get is like a potential, which means that first, like there is a decrease of the light intensity. That means that the protein will depolymerize. And then there is a change of trend, and there is like an increase and then a stabilization. So what we can suppose is like there is first a depolarization, then polymerization, and then a stabilization. And actually, what we are interested in is like the secondary phenomenon that appears in this kind of experimentation, which if we zoom on the change of trend, we get like some kind of oscillations mixed with the noise. And we want to know why and how can it be, because what does it mean to have oscillation for this kind of data? It means that like we have like a secondary effect. We have like a fast polymerization and depolarization process at the same time. Okay. So here are some graphs with different kind of initial data. So this graph is like with the 0.25 micromole data, micromole fibrils. This is like 0.35, 0.5, and 1 micromole. So we see that's another experimentation, and we see that we get like the same, kind of the same potential with like a depolarization, polymerization, and then stabilization. But in what's interesting, it's in all this experimentation, we get like some kind of more or less pronounced oscillations. For example, in the 0.35 experimentation, we get like a big amplitude for the oscillation. But in the 0.25 micromole experimentation, we get like a low amplitude for the oscillation that can be like blurred in the noise. So what's the motivation behind? So we want to have like a convincing argument for the presence of oscillations, and that will be that means like we have to do a signal analysis and statistical test. That's a work in actually that's a work in progress in collaboration with a statistician, Mark Hoffman, at Université Paris-Dauphine. And then we want also to have like a rigorous polymerization and depolarization model which oscillates. And the main goal for the physician and for the science is to get a better understanding of the size distribution evolution of polymer through times. Okay. So the numerals, let's start with the numerical signal analysis. So what are oscillations? Actually, in all the 1D, one-dimension signal we have, we can see like at low frequencies, we have like the trend. At high frequencies, we have like the noise from the experimentation. And then in the mid frequencies, we say that we have the oscillation. So we consider the oscillation to be like a level of energy in the mid frequencies. So how can we isolate and get more information about the oscillation? We use like a multi-resolution decomposition. So we project our signal in a wavelet basis, and in doing that, we can have like the information at a certain window of frequency. And we get like, for example, this is like the graph of the information at different resolution from the coarsest level to the highest level. At the highest level, we get actually our signal. And then at the coarsest level, we get only like the potential, which is a bit deformed, but yeah. And then we need to identify at which window of frequencies do we have the oscillations, and that can be solved because we can play with the window of frequencies, and we can also localize in the window of frequencies where there are the most energy. And for example, this graph shows like that the oscillation are mainly localized at the 10th window of frequencies. Okay, so now we just need to construct a test, a statistical test, saying how, if this is like a really oscillation, and this will be really oscillation if you compare like we find a measure which gives us a level of energy of from this resolution compared to the other resolution, and then we try to test our measure with the other resolution. Okay. Then that was for the numerical analysis, the signal analysis part. Then we want to construct like a model which oscillates. So in order to construct a model which oscillates, we started with like a chemical reaction which oscillates. The simplest chemical reaction which oscillates is like the Belousov-Zhabotinsky chemical reaction. Actually, this is like a simplified form of the Belousov-Zhabotinsky chemical reaction. It was introduced in 1951. So the Belousov-Zhabotinsky reaction is a reaction in a closed systems. So we have only 3 competitive spaces, the spaces A, B, and C. And actually, the spaces B dominate the spaces A. So that means like the spaces A will transform into the spaces B with a certain rate. The spaces B will transform in the spaces C with a certain rate K2. And the spaces C will transform in the spaces A in the certain rate K3. Okay? So we have kind of a cyclic exchange between all the spaces. So on the right, we have like the differential systems from this chemical reaction systems. One important fact is to say that these reactions are catalytic. What does it mean? It means like they need to be like an intervention between 2 species to have like a chemical reaction. And we hope that with this cycle reaction between these species, we have like an oscillation, a limit cycle which will appear, and then oscillation for the trajectory. And it's important to note also that we have like a mass conservation. So if there is no loss or gain in the systems, and that's translated in this kind of equation. So actually, if we have like initial conditions which are all positive, we can prove that the trajectory of the systems are periodic. It's actually, we get a fine proof in the book of Volpert and Kudjaev in 1985. And if we try to simulate the trajectory, we get like this kind of graph for this kind of reaction coefficient. And we get that all the trajectory are in the limit cycle. Okay. So we were happy because we found like a chemical reaction with a closed, in a closed system that oscillates. Then let's go back to our problem. So our problem is like an elegation problem. So it means like we want to find like a polymerization, depolymerization system which oscillates. So the polymerization system and depolymerization system was well synthesized in the Becker-Dorin cluster equations. So here we have like a polymer. So actually it can depolymerize, and then we have like a polymer of size 4, but with a monomers here, and it can polymerize in the other ways. So this kind of phenomenon is translated in this equation, this infinite dimensional systems, where Gi actually is the net rate at which I particle fibrils is converted to I plus 1 particle fibrils. So it's important to note that we have like 2 kinds of chemical reaction. This one is catalytic because the monomer C1 is necessary to get like polymerization, and this one is non-catalytic because actually with the depolymerization can happen without any exterior interference from the systems. And so we get like this difference between these 2 rates. And also the other thing to add, it's like in this system we have like a conservation law, which is like the total mass of the system is conserved through times. So this quantity is a constant. Okay. And now we are creating our systems. So we want like a like a systems of aggregation and fragmentation which oscillates, but we cannot like have like a purely aggregation, which means like some fibrils aggregate with another fibrils. That's like not physical, not physically, but not the biochemist thinks that it's not possible for our system. So what we do is like we introduce different kinds of particles. We need to have some kind of a cycle and exchange between the particles to have like oscillation for our system. So we add like two kinds of particles. We have like the V monomers, which is actually the normal monomers. It doesn't polymerize, but it's like used in the depolymerization here. And the V star monomer is like the infectious monomer, which polymerize here. And then there is an exchange between the V monomer, the normal monomer, and the infectious monomer. And we say that the normal monomer is transformed into an infectious monomer with the rate K. Okay? So let's note first that C1 represents the polymer of minimal size. We would have said like it's C0 or CJ, but C1 is not like one monomer. It's just a polymer which cannot depolymerize anymore. Okay? So then we introduce like the net rate at which I particle fibril is converted to I plus 1 particle fibril. And the difference with the Becker-Doring is here exactly, because now we have like a autocatalytic, not autocatalytic, but catalytic reaction for the depolymerization. Okay, so we can see close similarity between the differential systems, this differential system, and the Becker-Doring differential systems. The only difference is like we will have like the polymer of minimal size can only polymerize. And we have like two other species, the monomer which is like used for the depolymerization and the monomer which is used for the polymerization. Okay, and we still have like the conservation quantity, which is like the total mass of the systems. Okay. So what we want to do is to study these systems. So in order to study this system, we fix a maximal size. Actually, in these systems, we didn't fix a maximal size, but that does not mean that a fibril can aggregate at the infinity. It just means that we don't put like a maximal size. Here, we say like there is a maximal size of a fibril of size n. So it's a bit more easier to study because we don't have an infinite system, but then we have a finite genomical systems. And then we have also like another conserved quantity, which is like the total number of polymers. Okay. So when we do the numerical simulation of this system with a constant coefficient reaction, we obtain like a more or less damped oscillation, and then convergence to an equilibrium for the SLS measurements. So this is like the plot of the second moment of these systems. And the only difference between these two simulations is like we have like the same initial condition, so the same total mass and the same number of polymer in both systems, but we don't have the same parameters, and the only parameters which is different is like the K, which is the parameter which converts a normal monomer into an infectious one. So now we are interested in the study of the steady states and the dynamical behavior. So when we study the steady state, we have this kind of relation on all the rates, and this gives us that we have like a closed relation between closed equation between the polymer of size I and the polymer of size 1, which is a product of a quantity alpha I minus 1, etc., just until alpha 1. And alpha 1 actually is the ratio between the polymerization coefficient components and the depolymerization components in the systems. Okay. Then we were able to find like steady states for these systems. Actually, if like all the coefficients of the systems are constants, and we have like a real positive initial conditions, so number of polymers and total mass, then if the total mass over the number of polymers respect this really strict condition, then we have like the ratio between the polymerization components and over the depolymerization component is equal to 1, and then we can get a closed formula for all the quantity of the systems. The thing is, we just need to get like a closed formula for C1, V, and V star, since we can express all the Ci with the alpha and C1. But this is like actually this is a really strict condition. It means like the size distribution initially is centered on the middle of the on n over 2, which means like on the middle. So this is not really realistic. When n is like when in our system n is like really big, close to infinity. So this is not really realistic. And then if this condition is not true initially, then we get like actually a closed formula for the steady states, but alpha is given as the root of this polynomial. Okay. We get another information about the steady state of this information of these systems, is that what we want to study now is like we reduce the problem to study the root of this kind of polynomial. So using the lemma of Descartes' signs of rule, we can actually say, depending on the initial condition and the reaction coefficient, we can say the number of steady state we have in our system or not. Actually, when the initial condition respect this kind of relation, we have at most 2 positive steady states. But this is like this is actually an impossible condition, because we need to have like initial condition with bigger than n, and if n is close to infinity, then this is not respected. Then if we have like the initial condition which respect this kind of relation, then we have a unique positive steady state for the system with constant coefficient. And the other case is like if the initial condition respect this these 2 inequalities, then there is no steady state in the systems. So the most plausible case is only this one. Okay. So we are in reality we are sure that we have like a unique positive steady state. So now we found in studying our system, we found like a link with the Lotka-Volterra systems. I remind P0 is the total number of polymer, and then M actually is like the first order moment of the concentration of the size distribution, and we want that M oscillates. So here for these 2 equations, if we neglect C1 and if we neglect like Cn, so the concentration of polymer of size 1 and the concentration of polymer of size n, then this stuff is constant, this stuff is also constant, and then we get like the Lotka-Volterra systems where V star is the predator and V is the prey, and then we have oscillation between for V and V stars, and we have also oscillation for the M quantities. But the thing is, in the numerical simulation, we don't have like a like sustained oscillation. We have damped oscillation. This means that we actually this kind of perturbation really is really important for the behavior of our systems. Okay. Then the next step is to study the continuous model. So I just write what the continuous model will be looks like. So the continuous model is like a transport equation with linked to ODE equation. And this ODE, they have like a non-local term here. Okay. Okay. So now what's like the next steps? So the next steps is to extend the discrete model to nonlinear reaction coefficients. Or actually, what I just showed you is like only when the reaction coefficients are constants, but we can also do like the same for linear reaction coefficient. They can have the same behavior. So what we want to do is to find like the behavior for nonlinear reaction coefficients. And then the next step is also like to, because the continuous model is a limit of the discrete model, but we are not sure if like they will have like the same behavior, same oscillation behavior for the first or second moment of the continuous model. So we want to study the links between like between the behavior of the discrete model and the continuous model. Okay. Thank you.